Scientists said it was impossible. For 60 years, every fusion reactor on Earth hit the same invisible wall, a density limit that no one could break through, push the plasma too dense, and it tears itself apart. That was the rule until January 2026, when a team in China looked at that wall and punched straight through it.
Okay, you need to explain what that means, because I know fusion is supposed to be the holy grail of energy, but I honestly don't understand why we can't just do it already.
That's the perfect question, and the answer is one of the most fascinating engineering challenges in human history. So let's start from the very beginning. Fusion is what powers the sun. You take two hydrogen atoms, you smash them together at incredible speed, and they fuse into helium. When that happens, a tiny amount of mass converts directly into energy, following Einstein's famous equation, E equals mc squared.
And that tiny amount of mass produces a lot of energy?
An almost incomprehensible amount. One glass of fusion fuel, we're talking about heavy hydrogen extracted from seawater, contains the same energy as roughly 1 million gallons of gasoline. The fuel is essentially unlimited, the process produces no carbon emissions, and unlike nuclear fission, which is what current nuclear power plants use, fusion produces no long-lived radioactive waste.
So it's basically unlimited clean energy from water. Why don't we have this already?
Because recreating the conditions inside the sun is extraordinarily difficult. The core of our sun runs at about 15 million degrees Celsius, but it has a massive advantage. It has the crushing gravitational pressure of 330,000 Earths squeezing that plasma together. Here on Earth, we don't have that gravity, so we need to compensate by going even hotter. We're talking about 150 million degrees Celsius, 10 times hotter than the center of the sun.
10 times hotter than the sun. How do you even contain something that hot?
You can't use any physical container, because no material can survive those temperatures. The plasma would vaporize anything it touches. So scientists came up with an ingenious solution. They use magnetic fields. The most common design is called a tokamak, which is essentially a giant magnetic donut. Powerful magnets create invisible walls that suspend the plasma in midair, keeping it away from the reactor walls, while it burns at hundreds of millions of degrees.
That sounds incredibly delicate.
It is. And that brings us to the breakthrough. For decades, every tokamak has been limited by something called the Greenwald density limit. Basically, there's a maximum amount of fuel you can pack into the plasma before it becomes unstable. Think of it like trying to fill a balloon. You can add more and more air, but at some point, the pressure becomes too much and the balloon pops. In a tokamak, when you exceed the density limit, the plasma develops violent instabilities that kill the reaction and can actually damage the reactor itself.
And this limit has been a problem for 60 years?
Since the 1960s, it's been one of the fundamental barriers to achieving commercial fusion power. Because here's the thing, the amount of fusion energy you produce increases with the square of the plasma density. Double the density, you get 4 times the power output. So being stuck below this limit has been like trying to build a rocket engine but being told you can only fill the fuel tank halfway.
So what did the Chinese team actually do differently?
They used China's EAST reactor, which stands for Experimental Advanced Superconducting Tokamak. It's one of the most advanced fusion devices in the world, located in Hefei, China. The team, led by Professor Zhu Ping and Associate Professor Yan Ning, developed a completely new approach to starting up the plasma based on a theory that was proposed back in 2021 by French physicist Dominique Escande.
A French theory tested on a Chinese machine. I love that fusion research is so international.
It really is a global effort, and we'll get to the other major players in a moment, but the theory is called plasma wall self-organization, or PWSO. The key insight is genuinely surprising. The density limit isn't actually a hard physical law baked into the plasma physics. It's an artifact of how we've been starting up tokamak plasmas for 60 years. Think about that, generations of physicists assumed this was a fundamental constraint, and it turns out it was a procedural one.
That's wild. So what was everyone doing wrong?
Not wrong per se, but suboptimal. When you start a tokamak, you inject gas, ionize it into plasma, and begin heating. The traditional approach doesn't carefully manage the initial interaction between the hot plasma and the cold metal walls of the reactor. Escande's theory predicted that if you precisely control the fuel pressure and heating in a very specific sequence during startup, the plasma and the wall reach a harmonious equilibrium where physical sputtering, tiny particles knocked off the wall by the plasma, actually helps stabilize the system rather than destabilizing it. He called this the density-free regime.
The wall itself becomes part of the solution instead of the problem.
That's precisely it. And the East team proved it experimentally. They combined precise fuel pressure control with electron-cyclotron resonance heating, which uses microwaves to heat the electrons in the plasma. By getting the plasma wall interaction right from the very beginning, they prevented the harmful instabilities from developing in the first place. The result was stable plasma at densities far above the traditional Greenwald limit. No disruptions, no damage. And critically, this wasn't a fleeting moment. They maintained stable, high-density operation,
How far above the limit did they go?
significantly beyond it. The plasma remains stable at densities that would have caused catastrophic disruption under traditional startup procedures. And what makes this even more promising is that the technique is surprisingly simple. They didn't need new hardware or exotic materials. It's a new operating procedure, a new recipe for how you ignite and ramp up the plasma.
That's huge, but is it just a one-time lab trick? Or can this actually scale?
That's what makes this so significant. The technique is practical and scalable. It doesn't require exotic new hardware. It's a new operating procedure that could potentially be applied to any tokamak, including the massive ones being built right now. The results were published in Science Advances on January 1st, 2026, and the fusion community is genuinely excited because this addresses one of the core barriers to ignition.
Speaking of massive ones being built, what else is happening in fusion right now? Is everyone just building tokamaks?
Not at all. And this is where it gets really exciting. There are at least four major approaches to fusion happening simultaneously across the world right now, and 2025 was arguably the biggest year for fusion in history.
Walk me through them.
Let's start with the biggest project on Earth. Literally, ITER, which stands for International Thermonuclear Experimental Reactor, is being built in southern France. It's a collaboration between 35 nations, including the entire European Union, the United States, China, Japan, South Korea, Russia, and India. When completed, ITER will be the world's largest tokamak, designed to produce 500 megawatts of fusion power from just 50 megawatts of input heating. That's a tenfold energy gain, which would be an absolute game changer.
That sounds amazing. When is it going to be ready?
Well, that's the complicated part. ITER has been plagued by delays and cost overruns. The original budget was around 5 billion euros. The current estimate is over 20 billion. Construction started in 2010, and the original target for first plasma was 2025, but that's been pushed back significantly. There were serious manufacturing defects found in some of the reactor components that required extensive repairs. But the project is still moving forward, and it remains the single most important fusion experiment planned for this decade.
What about the Americans? What's the US doing?
Two huge things. First, the National Ignition Facility at Lawrence Livermore National Laboratory in California has been making incredible progress with a completely different approach. Instead of magnetic confinement, NIF uses laser-driven inertial confinement fusion. They fire 192 of the world's most powerful lasers simultaneously at a tiny pellet of hydrogen fuel, compressing it so fast and so hard that fusion ignites. In December 2022, they achieved the first ever fusion ignition, producing more energy from fusion than the lasers delivered to the target. And by 2025, they had pushed the energy output to 8.6 megajoules from 2.08 megajoules of laser energy. That's over 4 times more energy out than in.
4 times the energy back. Why isn't that on the news every day?
It should be, but here's the important nuance. The lasers themselves are incredibly inefficient. While the fusion reaction produced more energy than the lasers delivered to the target, the lasers consumed far more electricity than that. The 192 lasers drew about 400 megajoules from the power grid to deliver just 2 megajoules to the target, so the total wall plug efficiency is still deeply negative. It's a proof of concept, not a power plant, but the physics work. We can create a miniature star in a laboratory and extract net energy from it. That's the crucial point. And it was a genuine first in human history.
Is there a path from NIF's approach to actual power plants?
It's harder than the tokamak path, honestly. You'd need to fire these lasers 10 times per second at a continuous stream of fuel pellets, and you'd need much more efficient lasers. But the Department of Energy is funding new research centers specifically to explore inertial fusion energy, and laser technology is advancing rapidly, so don't count it out.
You said two huge things from the US. What's the second?
The private sector is going absolutely wild. The biggest name is Commonwealth Fusion Systems, or CFS, a startup that spun out of MIT. They've raised over $2 billion, and they're building a compact tokamak called Spark in Devens, Massachusetts. What makes Spark special is its magnets. CFS developed high-temperature superconducting magnets that are far more powerful than anything used in previous tokamaks, which means their reactor can be dramatically smaller while producing the same or better results. Spark is expected to achieve first plasma by the end of 2026, with the goal of demonstrating net energy gain in 2027.
A startup is building a fusion reactor.
Multiple startups, and this is what makes the current moment so different from previous decades. Helion Energy, backed by Sam Altman of OpenAI, has raised over $1 billion and already has a prototype reactor called Polaris running. Their approach is unique. Instead of trying to sustain a continuous fusion reaction, they rapidly compress plasma using magnetic fields, extract the energy directly as electricity without needing steam turbines, and then repeat. They actually have a power purchase agreement with Microsoft to deliver fusion electricity by 2028.
Microsoft signed a deal to buy fusion power.
They did. It's the first commercial fusion power purchase agreement in history. Whether Helion can actually deliver by 2028 is debated, but the fact that a company like Microsoft is willing to bet on it tells you something about where the technology stands. Then there's TAE Technologies, backed by Google, working on a completely different approach using particle beam-driven field-reversed configurations. There are over 40 private fusion companies worldwide now, collectively raising more than $7 billion. The fusion industry has gone from a handful of government labs to a global commercial race.
This feels like a tipping point. What about Europe beyond ITER?
Germany has been doing incredible work with a device called Wendelstein 7X, which is a different design called a stellarator. While a tokamak uses a combination of external magnets and an internal plasma current to confine the plasma, a stellarator uses only external magnets twisted into an incredibly complex shape. The advantage is that stellarators can theoretically run continuously, which is critical for a power plant. In May 2025, Wendelstein 7X set a world record for the fusion triple product, which is the combined measure of temperature, density, and confinement time during a 43-second plasma pulse. They achieved this by injecting frozen hydrogen pellets into the plasma at precisely timed intervals, a technique developed in collaboration with Oak Ridge National Laboratory in the United States.
Frozen hydrogen pellets?
Tiny frozen pellets about a millimeter across, injected like little bullets into the plasma to refuel it continuously, about 90 pellets over 43 seconds while the plasma burned at 30 million degrees Celsius. And then there's JET, the Joint European Torus in the UK, which held the fusion energy record for decades. In its final experiments before being decommissioned in 2024, JET produced 69 megajoules of fusion energy in a single pulse. That record still stands as the most energy ever produced by a controlled fusion reaction.
So you have China breaking density limits, America achieving ignition with lasers and building compact reactors with startups, Europe setting records with stellarators. Is fusion energy actually going to happen this time?
Here's what's different now compared to the old joke that fusion is always 30 years away. First, the physics is proven. Multiple facilities have now demonstrated that fusion works. NIF achieved ignition, JET produced record energy. The science is no longer the question. Second, the engineering is catching up fast. High temperature superconducting magnets, advanced materials, AI assisted plasma control, these are transformative technologies that didn't exist 10 years ago. Third, private money is flooding in. Over $7 billion from investors who expect returns, not just scientific papers. And fourth, the density limit breakthrough from East potentially removes one of the last fundamental physics barriers to commercial fusion.
What's the realistic timeline then?
If I had to bet, I'd say we'll see the first fusion-generated electricity on a commercial grid by the early to mid-2030s. CFS is targeting their ARC commercial power plant for the early 2030s. Helion claims they'll deliver power to Microsoft by 2028, though most experts think that's aggressive. ITER's full deuterium-tritium experiments are now scheduled for the 2030s. The key point is that for the first time in history, multiple independent paths to commercial fusion exist simultaneously.
And the fuel is basically seawater.
The primary fuel is deuterium, which is a heavy form of hydrogen that occurs naturally in seawater. About 1 in every 6,500 hydrogen atoms in the ocean is deuterium. The secondary fuel, tritium, is rarer and currently must be bred from lithium in the reactor itself, but lithium is abundant. With deuterium from the ocean and lithium from the Earth's crust, we have enough fusion fuel to power human civilization for literally millions of years.
What would that actually mean for the world? If fusion works at scale?
It changes everything. Think about the biggest problems facing humanity. Climate change. Fusion produces zero carbon emissions. Energy poverty, a single fusion plant could power 1 million homes. Water scarcity, with cheap, abundant energy, you can desalinate seawater at massive scale. Food production, vertical farms become economically viable anywhere on Earth. Space exploration, fusion propulsion could cut the trip to Mars from months to weeks. Access to cheap, abundant, clean energy is the single most transformative thing that could happen to human civilization.
And the fuel is basically seawater.
The primary fuel is deuterium, which is a heavy form of hydrogen that occurs naturally in seawater. About 1 in every 6,500 hydrogen atoms in the ocean is deuterium. The secondary fuel, tritium, is rarer and currently must be bred from lithium in the reactor itself, but lithium is abundant. With deuterium from the ocean and lithium from the Earth's crust, we have enough fusion fuel to power human civilization for literally millions of years.
Millions of years of clean energy from water and rock. That's the kind of future worth working toward.
And for the first time in 60 years, it's not just a dream. The old joke was that fusion is always 30 years away. But now we have ignition, we have record-breaking reactors, we have startups building hardware, we have the density limit broken, the artificial sun is getting close.